Hello everyone. As promised in my previous video that was on modeling systems with non-compressible fluid for controls, here I'm going to show you also simple modeling of thermal systems for controls, and again material is coming from Modern Control Engineering book by Katsuhiko Ogata. So as you know, we have three methods for heat transfer. We have conduction, convection, and radiation. And here we are going to only look at conduction and convection. You might say, why not radiation? Because in radiation, the heat flux is proportional to temperature to the power 4. And that basically is a nonlinear relation. So if I bring that into my systems, it is going to make my systems nonlinear, and then I cannot find a transfer function. So it's not really something that you want to study in control engineering. Plus, radiation actually shows itself when the temperatures of the surfaces are extremely hot. And that is not what you typically see in many control systems. So in most of the control systems, the heat transfer is done by conduction or convection. So that is the kind of thing that we are going to focus on. So if you remember, in conduction, the equation is this, that the heat flux dq over dt is equal to, and there is a negative sign here, but here I'm looking at the magnitude of it. If you don't have that magnitude, remember there is a negative sign here. K times A delta T over T, and some people, instead of this T, they use delta T over delta X. Or if you want to show a differential format of it, you can show dt over dx, the gradient of temperature with respect to the thickness of the material. So here A is the cross section of the material, T here, or delta X, is the thickness of the material along which there is a temperature gradient or change, and K is what we call thermal conductivity coefficient of the material. That depends on the material itself. Right? So some material have bigger numbers like aluminum, like copper, and some materials do not easily let the heat pass, right? So for instance, the heat insulation material, right? Or some kind of rubbers, some kind of specific, for instance, stones and so on. So ceramic is one of them, which has a very small K. So here we define thermal resistance similar to the way that we define resistance for an electric circuit, or resistance that we had for a fluid system, which you saw in a valve or in a pipe. We can also define a resistance for a thermal system, and that is basically the change in the temperature or temperature difference divided by the heat flow, the change in the heat flow. So the change in temperature difference divided by the change in heat flow. So it is basically like d of t or delta t divided by dq over dt. So that is the definition of resistance. Now, in the case of conduction, if you look at this formula, if I bring this dq over dt to the denominator of this, take then this k over a to the other side and t, then you can see that the resistance for a conductive material will be its thickness divided by its thermal conductivity times cross section. So T over Ka, that is your resistance for a material that is involved in conduction. Now for heat convection, as you remember, the heat convection equation, again, it says that the heat flow rate is equal to, is in magnitude, equal to H times A times delta T, where H is called the convective heat transfer coefficient. So let's say you have a hot object here, right? And this hot object is surrounded by air or any other fluid, right? And then The temperature of this fluid is what we call ambient temperature. Some notations use T infinity or T ambient. So delta T here is the difference between these two. That's T minus T ambient, correct? And then H, as I said, is the convective heat transfer coefficient, which depends on basically, to a good extent, the velocity of this, the relative velocity between this fluid and this object. That's why when we blow air over a hot object, we are going to increase this H. And A is the surface area that is in contact with the ambient fluid and is passing the heat to it. Okay, so it could, in this case, could be all the surrounding, all the surface area of the object. So in this case, if we want to find a formula for resistance, again, if I divide this delta T by this dq over dt, you see that 1 over HA is going to be your resistance when you have convection. So for conduction and convection, we have now a formula for a resistance, and we can consider them like a resistance that you had like in electric circuits. Now, other than a resistance, what else do you have in thermal systems that you can say it's similar to, for instance, an electric circuit? The other one is a storage. You know that any mass, when you give it heat, the temperature of it is going up, and it is going to store that energy in terms of increase in temperature. So here we can define a capacitance similar to capacitor that is used for storing electric energy. And capacitance is defined as the change in the heat divided by the change in the temperature. So if I know the heat Q, and if I divide it by delta T, that is the capacitance. Now, you know from basic thermodynamics or heat transfer that if you apply a total energy of Q, heat of Q joules, to some material with mass M and with a specific heat coefficient C, then the temperature of it in kelvins is going to go up by delta T, where delta T, MC, and Q are related by this formula. So in here, if I divide Q by delta T, clearly you see that the capacitance of any material is its mass times its specific heat. Okay, so for any material, we can also define a capacitance because it can store heat in terms of change in the temperature. Good. Now, one thing else that I need to emphasize is when you have a thermal system, like for instance this one that we're going to study, there are two ways that you can have the heat exchange between this system and the environment in general. One is, or you might call it three ways. One is that you have a heater in the system, and that heater is a heat source, and it generates heat and makes the system temperature go up, where the system stores that like a capacitor. Another way that the system exchanges heat with the environment is through convection or conduction with the environment, okay? So that you can model by a resistance. And another way that the heat energy can come into the system or gets out of the system is through the fluid flow. So it's not all convection, conduction, and heat source. It could also be through a flow of fluid that is coming into the system or leaving the system, okay? And those temperatures are not the same as the system temperature. For instance, if I insert a fluid into the system with a temperature T1 bigger than the system temperature T, that is like injecting heat into the system. Okay, so can I find the flow rate for this case, for the fluid flow? The answer is yes. How do we do that? Well, remember that the energy to raise temperature in a material with mass M and specific heat C is this guy here, Q equal MC delta T. Take a time derivative from both sides, and you see that the flow rate that comes with it is, since this delta T is a fixed number that you have, which is the difference between the temperature of the inlet flow and the system flow. The other parameter here in MC delta T that can change with respect to time is this guy M, and that is going to be M dot, or flow rate. So you see that a heat flow rate can come from a flow rate itself in terms of like meters cubed per second or liters per second or per minute or anything, times C times the difference between inlet or outlet flow and the system, basically material or system temperature. Okay, so this is another thing, and we are going to use that in the examples that you're going to see. So if before I go to my examples, if I want to compare a thermal system against mechanical and electrical systems, I can say that if a material does conduction or convection, I can define a resistance for it. Okay? Any mass that stores energy can be defined as a capacitor or capacitance. In thermal systems, we do not have any equivalent for inertia or inductance. So there is no equivalent to a mass or anything equivalent to an inductor. Okay, so pay attention to this part. The cause here can be considered the temperature difference, and the effect could be the heat flux. Or you can go the other way around, say the reason for temperature difference is heat flux. So heat flux is the cause and temperature difference is the effect, depending on how you look at it, right? If you're heating up a system, that heat is the cause and the change in temperature is the effect. But if, like this example that I said, the change in the temperature is the reason for getting a heat flux, right? Because you are inserting a fluid or anything that is hotter than the system or colder than the system, then the position can be swapped. In these formulations that you saw for the definitions of R and C, the way that we define them, we consider temperature difference to be the cause and we consider heat flux to be the effect. That's why when we define the resistance, resistance in electric circuit is the cause, which is voltage difference, divided by the effect, which is electric current. Now for a thermal system, we do a similar thing. We say resistance is the cause, which is delta T, divided by the heat flux, which is dQ over dt. Okay, and that is exactly what you saw over here. So in thermal systems, the cause and effect are defined the way that I just showed you, okay? And I want you to pay attention to that. I also want you to pay attention to the fact that we do not have any inductor or inertia in thermal systems. So if you change, basically, if you want to force a system to have a heat flux change, there is nothing that is gonna give you an opposing temperature difference or something. Okay, we don't have that. So now let's look at two examples here. Example one, a thermometer. Many places you probably have read that the temperature in thermometers behaves like a first order system. So for instance, if the initial temperature in a thermometer is like 20 degrees and you put it in a bath that the temperature is like 80 degrees, the way that it goes from this 20 degrees to this 80 degrees is an exponential, and it's like a first order system. Okay, so this is the behavior that you have seen. So why is it the first order system? Let me explain that to you. So here, if you look at the thermometer, which is inside this fluid or material with temperature T ambient, the only way of heat transfer between thermometer and this material is through convection. So the heat flow rate, dQ over dt, by the way, this capital Q here for us is the same as a small q, so I don't want you to get confused. So dQ over dt is going to be H A T of ambient minus T of the mercury or whatever it is inside the thermometer, right? That's the convection formula that we just had up here. So if that's the case, I write it. Now you know that this material inside this thermometer, mercury again, or whatever it is, any other material that these days are used, they are not all mercury anymore. Basically the flow rate is equal to the capacitance of that material times the change in the temperature, and this is coming from the formula of capacitance. If you look at the formula of capacitance, you see that C is Q over delta T, or if you look at it in terms of small changes, C is actually equal to basically dQ over dt divided by delta T. So if you cross multiply, you see that the heat rate or heat flux rate is capacitance times the change in temperature. So that is this formula here. But instead of delta T, of course, it's going to be dt over dt, right? Because if you want to write the equation in differential form, that cannot be delta T, that has to be d of T over dt. So the heat flux rate is going to be C times dt over dt, and that is exactly what this guy is. And that C, if you remember, and I showed you that C is m times C, mass times specific heat. Okay, so we have these two equations. Now what? Now, since these two are equal, they are both equal to the heat flow rate. So the left side of these equations are equal, therefore the right side should be equal. So we set them equal, and you get C dt over dt is equal to this HA T ambient minus T. Then that HAT with the negative sign, you can take it to this side. And if you do so, your equations become this. Your equation becomes this. And here we can define a time constant, and that is the coefficient of T, which is C over HA. And remember, this C is MC, so it's really M small c over HA. And that is the time constant of the system, where the unit is in seconds. If you write it, then your system equation becomes this in terms of tau. And if you take Laplace transform, of course, you are going to get tau s plus 1 times t equals t infinity of s. And of course, t over t infinity, which is the transfer function, is going to be 1 over tau s plus 1, which is absolutely a first order system. So you see the temperature of the thermometer over the ambient temperature. This is exactly a first order system. And you know, a first order system, the way that it behaves is exactly an exponential behavior, right? So this is basically, it is going to be T final minus T initial, right? Or in this case, T ambient minus T initial times e to the negative, let's make sure the root is negative 1 tau, so negative T over tau, and of course plus T naught. Plus or minus. Well, let's make sure the initial condition is satisfied. So it is going to be like this, this, and then plus T infinity. So in the beginning, as you can see, in the beginning T of 0, it is going to be equal to T naught. When T goes to infinity, it goes to T infinity. And exactly this is an exponential behavior. Okay, so this is for a thermometer, and the time constant of it, as you can see, depends on M, C, H, and A. So depend on the mass in it, depending on the specific heat in it, depending on this convection coefficient with the environment, and the cross section for the convection. Okay, so that is the time constant of a thermometer. Example 2, a little bit more complicated system. So here you have a a mixing chamber where there is some material inside with temperature T, and the inlet flow coming in with temperature T1, the outlet flow going out with temperature T2. The heater heat flow rate is H bar, of course. So these are all steady state scenarios. These are all the standard where everything is stationary and not changing. Okay? Yes? Now, what you do is, all of a sudden, you apply a little bit extra heat to the system or reduce the heat in the system. So you change the setting of the heater. Also, the input flow that comes in, the temperature of it changes also. As a result of that, the temperature of the system does change, and of course the output temperature does change. So in this case, I don't care about the output temperature much. What I care mostly about is the system temperature. So this is input number 1 of the system. This one is input number 2 of the system. These are the two controls I have. And the output of the system is that temperature T that I care about. Since I have one output and two inputs, I clearly need to find two transfer functions. One is T over H, the other one is T over T1. So I want to find both of these transfer functions. Now, the mass flow rate into the system and out of the system is shown by G. So G is m dot basically. That G is dm over dt. In and out of the system. The capacitance of all of this material inside the tank is C. The resistance R is considered for the convection that you have here between this outgoing material and the environment. So here you have R, here you have C. And the total mass in the tank is M, of course, where this capital C is small c times M, as you know. And we want to find those two transfer functions. So what would you do? As I said, in this system, there are three sources of heat flux. The heat flux directly because of the heater, the heat flux in, and the heat flux out. The heat flux out, I call it H naught. The heat flux in, which is dq over dt1, that is because of the inlet temperature change or difference between T1 and T. So GCT1 minus T is the inlet flow, right? And it could be negative if T1 is less than T, like in this case cold fluid, that could be a negative number, it's fine. So because T1 is a negative number or smaller than T. So remember I said that the heat flux because of the mass flow is this guy here. And in this case I call this dm over dt, I called it G. So it's GC delta T, and that is exactly what I have, that is delta T. Then we have a direct heat flux from the heater. That's input number 2, that's input number 1. And of course here we are giving some heat to the environment through the convection, and we call that HO. So the total heat balance is the two heats in minus the heat out is equal to the total heat flux. And if you remember, the heat flux is equal to the capacitance of the system times time derivative of temperature. And this is what we had over here by cross multiplying this. And that is exactly what we have down here. So this is my heat balance equation. Again, this term could be negative. Okay, so that could count as a negative temperature. It's fine. Now, if you look at this equation, here both of the inputs are inside of it. You can see both of the inputs inside this equation. So H is there and T1 is there. Also the output T and its derivative is there. So everything is good except for this guy, HO. We have to replace that HO, and once we replace it, then we can find the differential equation. So how do we do that? Here we said that we have a convection here. And convection comes with a resistance. So what is the resistance? If you remember, the resistance formula was what? The resistance was basically delta T over the heat flux. So in this case, it's delta T. What is delta T? It's basically the difference between T and T2 over the heat flux out, which is HO. That is the resistance. Now, how much was that resistance? It was 1 over HA for a convection, and we can consider it. But the reason I don't do it is because we have two separate H's in this system. One is this H, which is the change in the heat flux of the heater. So I don't want to use another H here and say that H is the convection coefficient. I want to hide it inside this R parameter, so you don't have to deal with two separate small H's. So from here, I can swap these H0 and R, and I can find the outgoing heat flux, and I can replace it right here. If I do that, then my equation becomes this. And now what I can do is I can go ahead and take all of my T's to the other side. It seemed like I missed a T2 term here. So I took all of my negative T terms to the other side, right? So this term and this term, I took them to the other side, and I took Laplace transform. So Laplace of dt over ds becomes S of t, S times C ts, and the other ones are there, these constants. And all of the other terms are on the other side. H is there, GCT1 is there, T2 over R is there. And so I write all of them. And from here, if I divide both sides by this coefficient of T, then I can find the transfer function for H and the transfer function for T1. And these are those transfer functions, which are both first order systems. Okay, and then you can consider T2 here. If T2 is something you can control, that could be like input number 3 of the system. Okay, or because that's the ambient temperature. Okay, so that T2 here is ambient temperature. I guess I just said that that is like a second output. Well, it could be a second output too, depending on how you model this part here and what relation exists between T and T2, right? So when this material goes from this part to this part, when it's exiting the chamber, what happens to it? You might say, well, I try to make that sure that T2 equals T, right? That's just the output temperature of the chamber. It's not the ambient temperature. Or no, when this material is getting out of the chamber until it gets to the environment, it cools down. Then yes, you can model that with a convection. You can consider conduction in it or something. So it depends on really what is it that you can do. So what is the ambient temperature? What is the temperature where this material is exchanged with the environment? Okay. So that is the question that we can determine. If it's something that we can control or it's out of our control, then we can say T2 here could be modeled like a disturbance to the system. So these two are the inputs of the system, T1 and C or H, and T2 here acts like a disturbance, because that's something, that ambient temperature, that is beyond my control. I cannot control that. So I can model it like a disturbance. Okay, in that case, if I want to model this as a block diagram, I can say that H is coming from this way, T1 is coming from this way, and T2 is coming from this way. and each one of them have their own transfer functions, right? Let me move them a little bit. So these are the two actual inputs of the system. And then before going to the actual system, you have your disturbance 2, which is T2, and this is multiplied by a simple gain of 1 over R. And that is added as the disturbance. And these are the inputs 1 and 2. And then the result of that is basically going to be T here, right? So these are those two transfer functions. This one for T1 is GC over that's this guy. And for H is this one. That sits there. And that 1 over R comes from this coefficient here. So you can model it like that. So this was a brief overview of thermal systems and modeling thermal systems for your controls, because if you want to consider heat transfer in your equations and in your control systems, you have to model them with resistance and capacitance, like I said, and find transfer function as long as they are acting linearly. Many times they are not linear, as I said. One example was radiation, but there are many other examples. And then you can design a controller or compensator for it. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.